In today's lecture, we'll be covering reaction mechanisms in coordination complexes, driving forces for ligand substitution reactions. So whenever you have a ligand substitution reaction, it's driven by thermodynamics. That is, the products being lower in energy than the reactants. And this is the same as with any reaction, right? Thermodynamics ultimately determines whether or not it's a spontaneous or non-spontaneous reaction, whether it's endothermic or exothermic. For ligand substitution reactions, we had talked about HSAB theory as being a qualitative way to look at trying to determine whether or not a ligand substitution reaction would be favorable or not. And in today's lecture, we'll be looking at ligand substitution reactions in a more quantitative way. So it's very important to keep in mind that ligand substitution reactions are equilibria unless one of the ligands is removed from the system, either through effervescence, which is gas evolution, or through precipitation of one of the ligands. And the direction of the reaction, or how heavily it is to one side or the other, depends on the equilibrium constant. So looking at these two cases here, with this hexa aqua iron 3 species and this silver 1 species, we can see that for iron, the equilibrium constant for the ligand substitution of a fluoride for a water ligand is 10 to the power 5, so that's very favorable, versus chloride, doing the very same ligand substitution, it's much smaller, it's 30. And this makes sense according to HSAB theory because iron in the +3 oxidation state is a relatively hard Lewis acid, and fluoride is a very hard Lewis base. So it would make sense that the hard Lewis acid and the hard Lewis base, so the iron and the fluoride, would form a stronger bond than, say, iron and a chloride. Silver 1, on the other hand, is quite soft, and this is actually reflected in the equilibrium constants for the formation of silver halides, shown right here. As you can see, the formation of silver fluoride has the lowest equilibrium constant. The formation of silver chloride is larger, silver bromide is even larger, and silver iodide is by far the largest with 10 to the power of 8. This is a demonstration of HSAB theory in practice. So the equilibrium constants for the formation of a new transition metal complex, they're called formation constants. And just like a normal equilibrium constant, the formation constant for a transition metal complex is the concentration of the products over the concentration of the reactants. Similarly, for the formation of the silver halides, in this case silver bromide, it's the concentration of the products over the concentration of the reactants. So these are really simplified cases where you're just either forming a complex from ions, or you're doing a single ligand substitution, right? In the case of the hexa aqua iron 3, we're substituting one aqua ligand for one halide ligand. But oftentimes we're going to be substituting multiple ligands at once. So in these cases, things get a little bit more complicated. So as an example of a more complicated ligand substitution reaction, let's look at the formation of tetraamine copper 2 from tetra aqua copper 2. So this is the overall reaction. You have your tetra aqua copper 2, it reacts with 4 equivalents of ammonia, and you do 4 ligand substitutions to form tetraamine copper 2. Pretty simple. However, this reaction is actually more complicated than it looks. The reaction can be broken down into 4 distinct steps, one for each ligand substitution. So what that means is you don't substitute all 4 ligands at once. It's a stepwise process. So in the first step, you have your starting material, so your tetra aqua copper 2, and it undergoes a ligand substitution with one equivalent of your ammonia. And that generates amine triaqua copper 2. Then this product from your first reaction becomes the reactant in your second reaction. So now this is the complex that undergoes a ligand substitution with ammonia, another equivalent of ammonia, to form diamine diaqua copper 2. and then the third ligand substitution occurs, and then the fourth ligand substitution occurs to finally form your final product, which is tetraamine copper 2. So each of these stepwise reactions has its own formation constant. That's called a stepwise formation constant. And why are we doing this, right? Yes, sure, it goes into 4 discrete steps, but overall, the reaction's the same. Well, it's important to know that it is actually 4 separate reactions occurring because each successive substitution makes a different product, and then that product becomes the reactant in the next ligand substitution. So each ligand substitution event needs to be modeled on its own because it's a completely different reaction with its own reactants and products. This is important because each step needs to be modeled on its own to be properly understood and so that you can properly understand the overall reaction. If you don't get the product you want, it's really important to know where things went wrong and why. So it's important to understand that when you're substituting multiple ligands, it's actually a series of reactions. And if you don't get what you want, you have to go back and look at which of those reactions failed. So how is the overall formation constant related to the stepwise formation constants? Well, it's actually the product of all the stepwise formation constants. So if you look at each individual substitution event, so each individual step of the reaction, you can construct the equilibrium constant or the stepwise formation constant for that step. So in the first ligand substitution event, this is denoted as K1, so it's the first ligand substitution. The stepwise formation constant for the first ligand substitution is K1, which is equal to the concentration of the product. In this case, this is the amine triaqua copper 2 over the concentration of your reactants, so that's the tetraaqua copper 2 and ammonia. Then your second step, so that's K2, the stepwise formation constant for the second ligand substitution is equal to now the product, which is diamine diaqua copper 2, the concentration of that, over the concentration of your reactants. In this case, your reactant here, the amine triaqua copper 2, is actually the product of the first reaction, first ligand substitution. And then you can see here it's ammonia is also one of the reactants. And so on and so forth. Same for K3, so your third ligand substitution, that's the stepwise formation constant for that. And then the fourth stepwise formation constant. And then for the overall reaction, so that's where you have your tetraaqua copper 2 reacting with 4 equivalents of ammonia to give tetraamine copper 2. The overall formation constant for that reaction is beta 4, and the 4 just denotes that it is the product of 4 formation constants, 4 stepwise formation constants. And you can see here K1 times K2 times K3 times K4 gives the concentration of the product, which is your tetraamine copper 2, over the product of the concentrations of all your reactants. So it's concentration of ammonia to the power of 4 because there's 4 equivalents, and your tetraaqua copper 2 compound. And just to convince you that the overall formation constant is indeed the product of all these stepwise formation constants, we're going to go through and look at which terms just cancel out. So for the first K1 stepwise formation constant, you can see here, this, when multiplied by K2, these terms will end up canceling out, right? They'll just end up being 1. And when you multiply K2 by K3, once again, these terms will just cancel out. And similarly, when you multiply K3 times K4, these terms cancel out. So overall, on top, you end up with tetraamine copper 2. And then underneath, you end up with your first starting material, so tetraaqua copper 2, and 1, 2, 3, 4 ammonia to the power of 4. So now we'll take a look at some of the quantitative values for the stepwise formation constants for the formation of tetraamine copper 2 from tetraaqua copper 2. So the first stepwise formation constant has a value of 10 to the power of 4.15. The second formation constant, 10 to the power of 3.5. The third stepwise formation constant, 10 to the power of 2.89. And the fourth stepwise formation constant is 10 to the power of 2.13. And then if you were to attempt to coordinate an additional ammonia, that formation constant is actually 10 to the power of minus 0.32. So that reaction is not favorable, and it is skewed towards the left, so towards the reactants. So overall, you should be able to identify a trend in these stepwise formation constants. And the overall trend is that they steadily decrease. This final formation constant for the coordination of the fifth ammonia ligand is a little bit of an outlier. It's much smaller than you would expect from the original trend. So why is that? Well, you actually have all of the knowledge already to be able to attempt answering this question. So as always, you kind of want to start with what is the d electron count on the copper 2? So copper 2 is a D9 complex. So is there anything special about D9 complexes that would make the formation of a 5-coordinate species unfavorable? Well, first off, that would make a 19 electron complex, which isn't unheard of, but wouldn't be as stable as, say, a 17 electron complex potentially, or definitely an 18 electron complex. So forming a 19 electron complex isn't always favorable. And another thing is that the D9 electronic configuration actually puts 2 electrons in a dz squared antibonding orbital. And these copper complexes tend to favor square planar geometries. So that's why the coordination of the fifth ammonia ligand is not favored. So now if we look at the overall formation constant for the synthesis of tetraamine copper 2 from tetraaqua copper 2, we can see it's the product of all the stepwise formation constants and equals 10 to the power of 12.67. So this is a very favorable reaction. And we will see in future slides that this decrease in magnitude for the stepwise formation constants as you undergo successive ligand substitutions. This is actually a general trend seen for all substitution reactions, and we'll explore why in the next slides. One of the reasons that successive stepwise formation constants steadily decrease, that is, K1 is generally larger than K2, which is larger than K3, etc., is for statistical reasons. So imagine you're doing a ligand substitution with a metal complex that has N aqua ligands, so N H2O ligands. There are N sites from which you can lose H2O. So if it's an octahedral complex, shown here, there are 6 sites from which you can do a ligand substitution with an L-type ligand. As substitutions occur, you get progressively fewer and fewer sites from which you can get a ligand substitution to occur. So there are fewer sites from which you can lose the water ligand. And eventually, once you've substituted all the water ligands except for one, there's only one site from which you can lose H2O. And this is very difficult to achieve, right? There's only one place where you can get a productive ligand substitution to occur. So it's difficult to achieve. This is related to entropy, so there are fewer degrees of freedom from which you can lose H2O, the more ligand substitutions that occur. Another way of thinking of this is that statistically, as you do more and more ligand substitutions, there are fewer sites from which you can get productive ligand substitution. There are a smaller percentage of collisions and vibrations that allow ligand substitution to occur. So there are fewer and fewer effective collisions that allow the reaction to proceed. But oftentimes we'll see that K1 is significantly larger than K2, which is significantly larger than K3, etc., more so than would be predicted by statistical factors alone. There are other factors that need to be considered as well, and we'll explore these. I would just like to mention that for most of the cases we're discussing, we're actually ignoring the difference in enthalpy due to metal ligand bond strengths. Often that will be decisive as to the direction a reaction will take, but not always, and it depends on temperature and a bunch of other factors as well. We're assuming in most of these cases that the enthalpic difference is small in comparison to the other factors we'll be looking at. But in reality, what you really need to do is take all the factors we're going to discuss as well as the differences in bond strengths together in order to look at whether a reaction will proceed or not, or why certain stepwise formation constants are larger than others. Steric factors could be a reason that K1 is greater than K2 is greater than K3, more so than would be predicted by statistical factors alone. Bulky ligands, if you're trying to do ligand substitutions with them, can prevent coordination of other bulky ligands and successive ligand substitution reactions depending on their demand for space about a metal center. So another way of phrasing this is that you can only pack so many ligands around a metal center, and at a certain point you just can't fit anymore. So an extreme example of this is generating a copper compound with this bipyridine variant, and you can see there are methyl groups ortho to the nitrogens in the bipyridine ligand. So these methyl groups here are in the ortho positions. So if you look at the K1, so the first stepwise formation constant, it readily replaces two aqua ligands, and you can generate this bipyridine variant with cis aqua ligands on copper. However, if you try to do the second ligand substitution, the stepwise formation constant is about 0. So the reaction doesn't actually occur. So why would that be? So one hint, it has to do for steric reasons. So how would we start approaching this kind of problem, right? Why is K2 0? Well, as always, it's very important to look at the d electron count of the metal center you're looking at. So for copper here, this copper center is D9, right? And it's D9, so it's either going to be tetrahedral or square planar. But in this case, I've drawn it square planar, so that's a bit of a hint. So this is a square planar compound. So if you were trying to coordinate two of these BIPI ligands, right? So the first one goes on no problem. What would happen if you tried to coordinate a second one? The problem is these methyl groups. We show them only as lines, but there's actually hydrogens coming off of them. And to illustrate that point, if I draw in all these hydrogens, you can see there's going to be a lot of steric strain generated by these methyl groups because they're pointing directly at each other. So because of this steric strain, the second ligand substitution generally will not occur, and it has a stepwise formation constant of 0. So you can only fit one of them on there. Now, say we were to change the copper 2 to zinc 2, would there be the same issue? So once again, what would be the d electron count of zinc? Well, the d electron count is d10. So is this going to be square planar? Probably not, right? It's probably going to be tetrahedral. So if we were to draw a tetrahedral complex, right? Once again, we're pretty confident we could fit one of those BIPI ligands on here, right? And here are your methyl groups. But the thing is with tetrahedral geometries, these different sets of ligands are going to be orthogonal to each other. So this BIPI ligand won't be in the same plane as this BIPI ligand. So these methyl groups are pointing above and below the zinc metal center, whereas these methyl groups are pointing along the sides. So there isn't that steric strain. Those methyl groups aren't pointing directly at each other. So the second BIPI ligand would be able to coordinate to zinc. And we saw coordinating two of these BIPI ligands on copper wasn't possible because the two BIPI ligands were in the exact same plane. So Coulombic factors could be another reason why K1 is greater than K2 is greater than K3, more so than would be predicted by statistics alone. And what this means is that if you're building up a lot of charge on your metal complex, that would be unfavorable. So one way this could occur is if you were replacing a neutral ligand with an anionic ligand. Say you had N plus positive charge on that initial metal complex. With each successive ligand substitution with an anionic ligand, you're going to lose some of that charge on your metal complex. The larger the N value, the more favorable it will be to do the initial anionic ligand substitution reaction. But as you start replacing more and more of those neutral ligands with anionic ligands, eventually you may come to the case where you end up with the charge turning from positive to 0, then being neutral, and then going negative. Well, if N is less than 0, then doing a ligand substitution with an anionic ligand is actually quite difficult. There's going to be a lot of repulsion between your metal complex and your anionic ligand when you're starting to do the ligand substitution, because you get significant repulsion between the two species that have like charges. So there's both kinetic and thermodynamic resistance to building up a lot of negative charge on a metal complex. There's big repulsion on bringing the two charged species together, which causes a very high activation barrier and causes the reaction to be very slow. And then the bonds are all weakened by repulsions from the already negatively charged complex and all the anionic ligands. Another way this could occur is if you're starting to do a ligand substitution of anionic ligands with neutral ligands. In this case, you would be building up a positive charge on your metal center. And eventually, it would become very difficult to lose an anionic ligand because you'd be building up so much positive charge on your metal center that it would be thermodynamically unfavorable. The metal would hold on to that anionic ligand very tightly, and you just wouldn't be able to do any more ligand substitutions. Every once in a while, however, you'll get an unusual case where K1 is greater than K2 is greater than K3, etc., is not the case. So sometimes there are exceptions to that general rule. This is often caused by a large change in the metal center, so that can be electronic and or structural. So an example of this would be the substitution of hexaquachromium 2 with 3 bipyridine ligands. If you look at the stepwise formation constants, K1 is actually smaller than K2, which is significantly greater than K3. And it would be really good practice to try drawing the lambda and delta versions of tris bipyridine chromium 2. So why is K2 so large? There has to be some sort of large electronic or structural change that is occurring. So is there a large difference between the aqua ligands and the bipyridine ligands? Well, one difference is that one's a chelate and one's a monodentate, but there's no inherent property of chelating ligands that demands they change the electronic structure of a metal center greatly when they bind. So there has to be something else at play. I mean, the chelate effect is definitely driving the ligand substitution to occur, but the unusual magnitude of K2 with respect to K1 has to be due to something else. So there has to be something else at play. Well, BIP is a relatively strong field ligand in comparison to water. So what can happen if you're replacing 6 relatively weak field ligands with 6 relatively strong field donors? So 3 chelating ligands, but the 6 nitrogen donors are relatively strong field in comparison to the water. So what can happen is that you can change your spin states. So that's actually what's happening here. The complex is going from high spin to low spin after the addition of the second BIP. And that's actually reflected in the second stepwise formation constant being larger than the first one. So the d electron count for chromium 2 is d4. But in the high spin state, the frontier orbitals will look like this. But if it transitions from high spin to low spin, the frontier orbitals will look like this. And this is a large change in the electronic structure of the chromium complex. So there's an increase in ligand field stabilization energy because this electron here is no longer populating an antibonding orbital. It now goes to the T2G. And you get an unexpected thermodynamic driving force for that second ligand substitution where the chromium goes from high spin to low spin. So this large change in electronic structure is what leads to the unexpected stepwise formation constant because it gives an extra thermodynamic driving force for that substitution to occur. So the reaction is skewed towards the right for the second ligand substitution, more so than would be predicted by statistical factors alone. And it is also important to note that this change in ligand field stabilization energy, this is an enthalpy-driven driving force, and it's not entropy. Now, it's important to note that the opposite could occur too. So if you're going from low spin to high spin, what you would end up with is a lower than expected stepwise formation constant. So when I'm asking you a question about unusual stepwise formation constants, you're going to have to use the knowledge you've gained in this class to determine is it going to be going from high spin to low spin or is it going from low spin to high spin, and that will depend on what the relative magnitudes of the stepwise formation constants will be and what ligands are being swapped out. So are you swapping out a higher field ligand for a weaker field ligand, so a stronger field ligand for a weaker field ligand, or are you swapping out a weaker field ligand for a stronger field ligand? Another unusual case of stepwise formation constants is illustrated in the synthesis of tetrabromocadmate 2. So starting from hexaaqua cadmium 2, if you do 4 ligand substitutions with bromide, you can generate tetrabromocadmate 2. If you look at the stepwise formation constants, K1 is larger than K2, which is larger than K3, but K4 is actually larger than K3. So which of these stepwise formation constants is unusual? Well, you should be able to identify that K4 is the one that sticks out. So can you think of why K4 might be larger than K3? Can you think of a reason as to why that could be? Now, just to let you know, this is a different case than before. Bromides are weak field ligands, as are water ligands. So it's not a transition from high spin to low spin or low spin to high spin. So what's actually happening is you're getting a change in your coordination number on the 4th ligand substitution. And you can see you're going from triaqua tribromocadmate 2 to tetrabromocadmate 2. And what you should be able to recognize is you're going from octahedral to tetrahedral. So the change of coordination geometry is actually releasing a lot of extra ligands, right? You're going from coordination number of 6 down to 4. So this releases a lot of ligands. So when you're drawing out your balance equation, you have to put in 3 water molecules on the right side. And because of this, there's a strong entropic driving force for this reaction. So the thermodynamic driving force comes from an increase in entropy and disorder in the system. It's important to note that the reverse could occur as well. So if you are going from a tetrahedral to an octahedral coordination geometry, you would get more order in the system. You'd have more ligands on the left side and more molecules on the left side than you would have on the right side. So what would you expect to see in that case? Well, you would expect to see a much smaller stepwise formation constant than you would normally get just from statistical reasons alone. Now, just to point out, so the formation of tetrabromocadmate, you are building up a lot of negative charge on the cadmium center, but the cadmium is pretty soft, whereas water is pretty hard. So cadmium bromide bonds are stronger than cadmium oxygen bonds. So that makes up for the fact that this is a coulombically unfavorable reaction. So you need to start getting used to the idea that I can start asking questions where you need to use knowledge to identify an exception to a trend and try to explain it. So for an example, you could be given a reaction where you're forming a complex with multiple ligand substitutions, and I could give you the stepwise formation constants and ask you if there are any strange outliers, or what do you think is happening, or what is the key step in this type of reaction. So you're going to need to be able to explain what the general trend should be, and then explain what is different in a case that's not following that general trend. This concludes today's lecture. If anything was unclear, please feel free to ask questions during office hours or try rereading the textbook to clarify concepts. And as always, there are some useful websites and resources in the links below to help with understanding some of the concepts that were presented today.